Example 2, Chapter 3, Fluid Mechanics. The balloon in this figure is being filled through section 1 as shown here, where the area is A1. So at T, for example, 0, A equals to the cross section area velocity is v1 and fluid density is rho. The average density within the balloon is average Find an expression for the rate of change of system mass within the balloon at this instant. So find an expression for the rate of change of system mass within the balloon at this instant. At first, we should write the Reynolds transport theorem. Plus in this case we cannot eliminate the first integration because we have change in control volume as we said before, so then the control volume change is a relation of the change of RT, so we can write this relation for the first expression. So we have d on dt, integration of rho, which is rho t, dv, we should calculate this dv also, dv, and let me write v equals to r cube. So dv on dt equals to 4pr to dr, which is r a function of t. So dv equals to 4pr2 dr dt. So to calculate the first expression of right hand side, we can write d on dt integration of on control volume rho dv d on. It is not necessary to replacement dv with this expression. We can write the rho v equals to d on dt rho, which is a time of t, and the volume r also is a time of a function of t. So we can write the Reynolds transport theorem with respect to this. We had this relation dv on dt d on dt integration plus sigma beta m dot I out minus sigma beta m dot I in. So m is b and beta is dm on m and equal to 1. So dm on dt, from previous we calculated the first expression, which was rho t plus we don't have in outlet flow, we have just inlet flow equals to minus rho 1 a 1 v1. In the relation given, the answer to the question that was asked, actually by the conservation law of mass, the answer could be written as the system. We have also the relation for conservation of mass equals to 0. With replacing, we can obtain this relation for the problem. Equals to rho 1 that's right. This is the first order ordinary differential equation relating gas density and balloon radius. It could form part of an engineering analysis of balloon inflation. It cannot be solved without further use of mechanics of thermodynamics to relate four unknowns rho v, rho 1, v1 and r. So we have a should relation between rho 1, v1 and rho v and r.